In this video, we are going to dive into the reaction mechanism for converting 3,3-dimethyl-1-butene to 2,3-dimethyl-2-butanol, a process that involves both electrophilic addition and carbocation rearrangement. So let's break it down step by step. The carbon-carbon double bond in 3,3-dimethyl-1-butene contains a pi bond. That's a region of high electron density. The pi electrons are more loosely held than the sigma electron in a single bond. Therefore, the region acts as a nucleophile or a site that can donate electron. H2SO4 serves as the acid catalyst in this reaction. Within the H2SO4 molecule, the oxygen atoms are more electronegative than the hydrogen atoms. So it's leading to the partial negative charge on the oxygen atoms and partial positive charge on the hydrogen atoms. This electronegativity difference makes the H atoms electrophilic site, exhibiting a partial positive charge and attracting electrons from a nucleophile such as alkenes. The 2 pi electron from 3,3-dimethyl-1-butene carbon-carbon double bond attack one of the H atoms of the H2SO4. The pi bond is broken as a result of this process. The 2 sigma electrons between H and O atoms are pushed to the more electronegative O atom to form HSO4- ion. The nucleophilic attack by the 3,3-dimethyl-1-butene pi bond result in the formation of new sigma bond between the C atom with more H atoms at 3,3-dimethyl-1-butene carbon-carbon double bond and the H atom from the H2SO4, breaking the pi bond in the process. According to Markovnikov rule, the H atom from H2SO4 will add to the C atom at the carbon-carbon double bond with more H atom. The application of Markovnikov rule helps predict the major product form because the ratio selectivity is determined by the stability of the carbocation intermediate formed during the reaction. Thus, secondary carbocation is more stable than primary carbocation for this step because the more alkyl substituted carbocation can better stabilize the positive charge through hyperconjunction and inductive effect. Step 2 is rearrangement. In the carbocation intermediate, a neighboring H atom along with its bonding electrons migrates to the C atom carrying the positive charge. This results in forming a new carbocation at a more stable position. The hydride ion shift from the C adjacent to the positively charged carbon to the carbon bearing the positive charge. The hydride ion and the positive charge migration occur simultaneously. After the 1,2 hydride shift, a more stable carbocation is formed. In this case, the positive charge is located on a tertiary carbon, which is more stable than previous secondary carbocation. The rearrangement allows for a more substituted and therefore more stable carbocation, leading to a more efficient and selective reaction. Step 3, formation of protonated alcohol by adding water. Water is the nucleophile in this reaction. The water molecule attacks the positively charged carbon formed in the previous step using one of its lone pair. This forms a new carbon-oxygen bond. The O atom bears a positive charge due to forming the new carbon-oxygen bond. Step 4. Deprotonation of protonated alcohol. In the final step, a proton is abstracted from the positively charged oxygen, forming the final product is 2,3-dimethyl-2-butanol. The HSO4- is a base that attacks the proton on the positively charged O atom. The HO bond breaks and electrons from the sigma bond are pushed towards the O atom. The final product, 2,3-dimethyl-2-butanol, is formed after deprotonation. It is important to note that using sulfuric acid as a catalyst is crucial in facilitating the protonation of the alkene and promoting the subsequent nucleophilic attack by water. The acid catalyst is regenerated at the end of the reaction, making it a catalytic process.